let's evaluate the following integral of e to minus the floor of x dx between 0 and plus infinity. Here we have two things to do. First, we need to show that this one exists. Okay, and next we're gonna try to evaluate this integral. So let's first see if we can prove that this one exists. Okay, we're gonna use our usual techniques. Let's split this integral between 0 and 1 e to minus the floor of x dx and 1 plus infinity e to minus the floor of x dx. Okay, here this one is a definite integral and it does exist all the time. So the issue is here. We had to split between 0 and 1 plus infinity to use some comparison tests. Okay, so the key idea here is that e to minus the floor of x is less than e to minus x plus 1. Okay, and if we integrate between 1 and plus infinity, okay, we see that this one is convergent. We don't need to evaluate that. We can compute it exactly, and therefore by the comparison test this one is convergent. Okay, so our integral here is convergent. So that's what we have to do. So we can't just compute this one. We need to prove that it does exist. Okay, next we're gonna apply the definition of the improper integral. So here the limit as x goes to infinity of the integral between 0 and x of e to minus the floor of t dt. Okay, we focus on this one here first. Okay, the next thing that we have to see is that we will split this interval 0x into small intervals or subdivisions where the floor of t is easy to compute. Okay, so one key idea is that if n is the floor of x, okay, then as n goes to infinity, x will go to infinity as well. Okay, so this is the key that we're going to use here. Okay, so if x goes to infinity, then n, which is the floor of x, will go to infinity. Easy to compute using the squeeze theorem. Okay, now we can split this interval, this integral 0x e to minus the floor of t dt into the following manner. So between 0 and 1, e to minus the floor of t dt plus the interval 1, 2, e to minus t dt, and etc. until we get into n minus 1 and n e to minus t dt. Here n is the floor of x. Now using this fact here, this one here, so we have this limit is the limit as n goes to infinity of this integral between 0 and n of e to minus the floor of t dt. And using this sum here, okay, we see that we can compute this one easily. Okay, here this is just 0 because the floor of t between 0 and 1 is 0 and e to 0 is 1. So we have 1. So here the limit as n goes to infinity of here 1 plus e to minus 1 plus e to minus 2, etc. until the last one, which is e to minus n minus 1. Okay, now this is a geometric series with ratio 1 over e. Okay, So here we can rewrite this one in the following manner. So the limit as n goes to infinity of 1 minus e to n over 1 minus e to minus 1 minus n. Okay, here this one will go to 0. Okay, as n goes to infinity, because it's less than 1, and therefore our limit is going to be 1 over 1 minus e to minus 1, or we can rewrite it as e over e to minus 1. Okay, therefore my integral is equal to e over e minus 1. So this is the value of my integral. Okay, the key idea is that we need to prove that this integral exists, and after that we use the properties of the floor function to decompose this integral after we have done the definition of the limit of the improper integral. Okay, and this is the value. Thank you very much.